maximum. The next topic I am going to discuss is how to find maximum and minimum of a function of two variables. We are given a function of two variables and we have to find the maximum and minimum values of this function subject to some given condition. Maximum and minimum of a function of two variables satisfying a given condition. Let p is equal to fxy be a given function and gxy equal to k be a given condition. We have to maximize or minimize p equal to fxy such that this condition is satisfied. We have to maximize this function such that this condition is satisfied. So what we do is we eliminate one of the two variables from this function using this condition and express this function as a function of a single variable. So what we do is we eliminate one of the variables from this function using this condition and express this function as a function of a single variable and proceed as usual. That is, express one as a function of single variable using 2 and proceed as usual. So this will be the method we will follow. We will express this function as a function of a single variable using this, and we know how to find maximum and minimum for a function of a single variable. We have already discussed this. Now first question I am going to take up is divide 64 into two parts such that the sum of cubes of two parts is minimum. We have to divide 64 into two parts such that sum of cubes of those parts is minimum. Let xy be the two parts. Therefore, x plus y is equal to 64. And we have to minimize the sum of the cubes of these two parts. So sum, let s be equal to sum of cubes of these parts. That is x cube plus y cube. We have to minimize this. Divide 64 into two parts such that sum of cubes of these parts, that is sum of cubes of x and y, is minimum. We have to minimize s. Now let this be 1, this be 2. Now first step will be we will express this function as a function of a single variable using this condition. So what we do is we write s is equal to x cube plus, now eliminate y. Y will be 64 minus x. 64 minus x. At this step we eliminate that variable which does not complicate the question. The question remains simple. In this case the question is symmetrical in x and y, so we can eliminate any. But in other questions, just think for a minute which variable should we eliminate, which will keep the question simple. So now the question has been expressed as a function of a single variable. Now we proceed as usual. Find the first derivative, ds by dx. ds by dx is 3x square plus 3 into 64 minus x whole square into d by dx of 64 minus x. d by dx of 64 is 0 and d by dx of minus x is minus 1. So this is equal to 3 into x square minus 64 minus x whole square. Now simplify this. This will be 3 into a square minus b square. This will be a minus b into a plus b. This is a minus 64 plus x into a plus b. X plus 64 minus x. this x cancels with this, and we are left with 3 into 2x minus 64 into 64. So this is equal to 2 is common. So we have 6 into 64. 6 into 64 is 384. So 384 into x minus 32. So ds by dx is equal to 0 implies x is equal to 32. So we have only one critical point. Now if this critical point is a point of local maximum, then it will also be a absolute maximum. And if it is a point of local minimum, then it will also be a point of absolute minimum. So what we do is we find d2s by dx square. d2s by dx square is 384. Differential of this is 1, this is 0. So 384, which is greater than 0. Therefore, d2s by dx square at x is equal to 32 is greater than 0. Therefore, x equal to 32 is a point of local minimum. But since we have only a single point, this will also be a point of absolute minimum. Therefore, x equal to 32 is a point of minimum. Therefore, x equal to 32 is a point of minimum. And y is equal to 64 minus x. And this is equal to 64 minus 32. That is 32. Therefore, x is equal to 32 and y is equal to 32 will give this sum as a minimum. The sum will be minimum if x is 32 and y is 32. Answer. So what we do is we first express this function as a function of a single variable and proceed as usual. And here we must note that since we are having only one point as a critical point, therefore if this point is a point of local minimum, it will also be a point of absolute minimum. So this will be the minimum value. Next is find two positive numbers x and y such that their sum is 35 and the product x square y5 is maximum. So sum of two numbers x plus y is 35 and product p is equal to x square y5 has to be maximized. P. We have to maximize p. Let this be 1 and this be 2. Now first step is we will express p as a function of a single variable. Now we eliminate one of the variables. Now here we must think for a minute which variable we should eliminate, which will keep this question simple. So what we do is we will eliminate x in this case. X will be 35 minus y. So this will be 35 minus y whole square and this will be y to the power of 5. If we eliminate say y instead of x, we will have x square into this will be 35 minus x whole to the power of 5. And on differentiating we will have to expand 35 minus x to the power of 4, which will be complicated. Here we will have only to expand this. We must think for a minute which variable has to be eliminated. Now we eliminate x and we get this. Now we maximize p. So dp by dy is equal to first function into differentiation of second. Differentiation of y5 is 5y4 We are differentiating with respect to y. So differential in the function will be 1 plus y5 into differential of this. Differential of this will be 2 into 35 minus y into differential of n function. Differential of n function will be differential of 35 is 0 and differential of y will be minus 1. So what we get is we have 35 minus y is common and we are left with 5y4 into 35 minus y. Minus 35 minus y is common, minus 2y5. Minus 2y5. So this is equal to 35 minus y into y to the power of 4 is common and we are left with 5 into 35 is 175. 175 minus 5y minus 2y. y4 is common. So this is equal to 35 minus y into y4 into 175 minus 7y. Now let dp by dy is equal to 0. This implies y is equal to 35 or y is equal to 0 or y is equal to 175 by 7. 175 over 7 is 25. Y is equal to 0, rejected because numbers are given to be positive. Therefore, they cannot be 0. And y is equal to 35 implies x is equal to 0 from 1. Therefore, this is also rejected because x cannot be 0. Because if we put y is equal to 35 here, x will be 0. But x cannot be 0 because the numbers are given to be positive. Therefore, they cannot be 0. We are left with y is equal to 25. This is rejected. This is rejected. So we have only single critical point. Now, if this point is a point of local maximum, it will also be an absolute maximum. If it is a local minimum, it will also be an absolute minimum. Therefore, we will now find whether y is equal to 25 is a maximum or minimum. For this, we will use first derivative test because second derivative test will be difficult to use because this is the product of three functions. So to find second derivative will be lengthy. So here we use first derivative test. For y less than 25, sign of first derivative dp by dy is, we have to determine the sign of first derivative. And for y greater than 25, we again have to find the sign of the first derivative. Now for y less than 25, now this is the number line. This is 0, this is 35 and this is 25. So for y less than 25, we can take any value in this interval. Take it as 10. Say at 10, this is positive, this is positive. 10 into this is positive. So this is positive. And in this interval, we can take any value, that is, let it be 30. So at 30, what we see is 35 minus 30 is positive. This is positive. 30 into 7 is 200. So this is negative. Negative. Overall sign is negative. So what we note is dp by dy is changing its sign from positive to negative. That is, the function is changing its trend from positive, that is increasing, to decreasing. Increasing to decreasing, that is rising to falling. So this will be a point of maximum. Therefore, y is equal to 25 is a point of local maximum, but local maximum will also be an absolute maximum in this case. So this is a point of maximum, and therefore y is equal to 25 and x is equal to 35 minus y, that is 35 minus 25, that is 10. So x is 10. This will be the answer. This product will be maximum if x is 10 and y is 25. And if you want to find the value of this product, then put it here, x equal to 10 and y is 25, you will get the value of the maximum product. Now these questions you can try yourself. Their sum is 60 and product, this is maximum. Sum is 25, product is maximum. Sum is 14 and sum of squares is minimum. That is, x square plus y square is minimum. These problems you can try yourself. Now we take up some practical questions. Show that of all the rectangles with a given perimeter, the square has the largest area. And second part is, show that of all the rectangles with a given area, now the area is given, the square has the smallest perimeter. In this case, perimeter is given and we have to maximize the area. In this case, area is given and we have to minimize the perimeter. Let x and y be the length and breadth of the rectangle. Then its perimeter is given. Then perimeter of the rectangle is 2x plus y. Sum of lengths and breadths of all the sides, that is 2x plus y, is equal to p. This is given. This is fixed. This is constant. And area has to be maximized. And area A is equal to length into breadth. Let this be 1, this be 2. We have to maximize A subject to condition 1, that the perimeter remains fixed. We have to maximize A subject to this condition, that is, the perimeter remains fixed. So first of all, we will express this function, which is a function of two variables, as a function of a single variable using this condition. So what we do is A is equal to x into y, but y is equal to p by 2. Take this to the other side. P by 2 minus x. P by 2 minus x. Y is p by 2 minus x. So this is equal to x into, eliminate y, p by 2 minus x. And therefore now this is a function of single variable. This can be written as 1 by 2 px minus x square. So we find its maximum value, dA by dx. dA by dx is 1 by 2 p, and differential of x is 1 minus 2x. Therefore dA by dx is equal to 0, implies p by 2 minus 2x. p by 2 minus 2x is 0, and this implies x is equal to 2x is equal to p by 2. Therefore, x is p by 4. So, x is equal to p by 4. Now, we find d2a by dx square. d2a by dx square is differential of this is 0 and differential of this is minus 2. Therefore, d2a by dx square at x is equal to p by 4 is equal to minus 2, which is negative. Therefore, x is equal to p by 4 is a point of maximum, local maximum, but we have a single point here, so it will also be a point of absolute maximum. So this will be a point of maximum, and therefore y is equal to, y is p by 2 minus x, p by 2 minus x is equal to p by 2 minus p by 4 is equal to p by 4. Therefore, for maximum area, x is equal to p by 4 and y is also equal to p by 4. Therefore, for maximum area, length must be p by 4 and breadth is also equal to p by 4. Therefore, x is equal to y, and therefore rectangle must be a square because its length and breadth are equal. Therefore, it must be a square. Therefore, a rectangle with a given perimeter has maximum area when it is a square. Now I take up the second part. Now second part is show that of all the rectangles with a given area, the square has the smallest perimeter. Second part is let x be the length and y be the breadth of the rectangle. Let x be the length and y be the breadth of the rectangle. Then show that of all the rectangles with a given area. Now area of the rectangle is given, that is x into y is equal to a is given, that is it is fixed, it is constant. Of a given area, the square has the smallest perimeter. Now perimeter of this rectangle is twice x plus y. We have to minimize p subject to the condition 1. Say this as 1 and this as 2. So what we do is we first express 2 as a function of a single variable. P is equal to 2 into x plus y, and x into y is equal to a, and therefore y must be equal to a by x. So this is equal to 2 into x plus, we put y equal to a by x. Now this is a function of a single variable, and we proceed as usual. We find the first derivative, dp by dx. dp by dx is 2 into differential of x is 1, and differential 1 by x is minus 1 by x square. This will be minus a by x square. Put dp by dx equal to 0. This implies a by x square is equal to 1, and this implies this is 0. Therefore, a by x square is 1, and therefore x square is equal to a, and this implies x is equal to root a. X is root a. Now we shall verify that x equal to under root a is a point of minimum. We have to minimize p. So we verify that x equal to under root a is a point of minimum. What we do is we find d2p by dx square. Now from 4, d2p by dx square is 2 into differential of 1 is 0, and differential of a over x square is a into x to the power of minus 2. So minus 2 over x cube. So this will be minus minus plus 2a by x cube. And therefore d2p by dx square at x is equal to root a is equal to 4a over a root a, that is 4 by root a. Root a cube is a root a cancels, we get 4 over root a, which is greater than 0. Therefore x is equal to root a is a point of minimum. This is a point of minimum. And when x is root a, from 1 we have 1 implies y is equal to a over x. And this is equal to a over root a is equal to root a. Therefore x is equal to root a is equal to y. Therefore given rectangle is a square. Therefore rectangle must be a square. Hence proved. Now next question is a rectangular sheet of tin 45 centimeter by 24 centimeter. Let this be the rectangular sheet of tin. A rectangular sheet of tin of length 45 centimeters and its breadth is 24 centimeters. A rectangular sheet of tin 45 centimeter by 24 centimeter is to be made into a box without top by cutting off squares from each corner. We have to cut squares from each corner. Let this be the square that is being cut off. Let x be the length of the square to be cut off by cutting off squares from each corner and folding up the flaps. These flaps will be folded and we will get a rectangular box without top. We will fold this remaining portion, folding up the flaps. What should be the size of the square to be cut off so that the volume of the box is maximum possible? Volume of the box is maximum possible. Also find the maximum volume. We have a rectangular sheet of tin whose length is 45 centimeters and width is 24 centimeters. We are cutting a square from each of the 4 corners. So length of the flap, this flap will be length of box. Length of the box will be this much and width of the box will be this much. Let this be A, B, C, D. So length of the box is equal to CD is equal to, how much is CD? CD will be, this x is gone, this x has been cut off. So we are left with 45 minus 2x. 45 minus, this will be the length of the box and the width of the box will be this. Let this be E, this be F. So width of the box is equal to EF, is equal to EF, and this will be equal to 24 minus x, that is 24 minus 2x. So this will be the length of the box and this will be the width of the box. A rectangular sheet of tin 45 centimeter by 24 centimeter is to be made into a box without a top by cutting off squares from each corner and folding up the flaps. What should be the size of the square to be cut off? We have to find x so that the volume of the box is maximum possible. Volume of the box. Volume of the box will be length into breadth into height. So length of the box is this much. 45 minus 2x. Width of the box will be this much. So this will be 24 minus 2x. And we are folding up this flap. This flap will be vertical. So height of the box will be x. This is x, this is x, this is x, and this is x. So height of the box will be this much. That is x. And we have to now maximize this. We have now to maximize v. So first we find dv by dx. dv by dx. We differentiate this. 45 minus 2x into 24 minus 2x into differential of this. This is 1. How we differentiate? Product of three functions. So first is differentiate this, leave the other two as they are. Differentiate this, leave the other two as they are. And then differentiate this and leave the other two as they are. First differentiate this, other two will remain same. Then differentiate this, other two will remain same. Then differentiate this, other two will remain same. You can see the side sheet. Plus 45 minus 2x into x into differential of this will be minus 2. Plus, now we will differentiate this and leave the other two as they are. 24 minus 2x into x and differential of 45 minus 2x is minus 2. So this is equal to 2 is common. And we are left with 45 minus 2x into 12 minus 2 is common, minus x into 45 minus 2x minus x into 24 minus 2x. This simplifies into 45 into 12 is 540 minus 45x minus 24x minus minus plus 2x square minus 45x minus minus plus 2x square minus 24x plus 2x square, and this is equal to twice into. Now we collect the quotients of x square. 2x square, 2x square, 2x square. This is 6x square. Now we take the terms involving x. Minus 45 minus 24x minus 45x minus 24x. So this is 90 plus 48. That is minus 138x. Minus 138x. Now we are left with only constant term. This is constant. Only constant is 540. So this is equal to 6 is common. So we get 12 into x square minus 6 2s are 12, 6 3s are 18 plus 9 6 are 54, 90. So put dv by dx equal to 0. This implies x square minus 23x plus 90 is equal to 0. Now 90 can be factorized as 2 into 45, 3 into 15. 3 3s are 9, 9 2s are 18. 18 plus 5 is 23. So we can write this as x square minus 18x minus 5x. Sum is minus 23 and product is 90. So 90 is equal to 0. And this can be written as x is common, x minus 18. This is minus 5 is common, x minus 18. This is equal to 0. This implies x minus 5 into x minus 18 is equal to 0. And this implies x is equal to 5 or 18. Therefore, x is equal to 5 and 18. You can see the previous sheet as a side sheet. Now we find the second derivative, d2v by dx square. This is equal to 2 implies this is d by dx of 12 into dv by dx is 12 into x square minus 23x plus 90. So this is equal to 12 into 2x minus 23. Therefore, d2v by dx square at x is equal to 5 is 12 into 2 into 5 minus 23, which is negative. This is 10, 10 minus 23 is negative. Therefore, x equal to 5 is a point of maximum. X equal to 18 is rejected. Because if we cut a square of length 18 from each corner, there will be no tin sheet left. Because length of the tin sheet is 24 centimeters. So a square of 18 centimeter cannot be cut. 18 plus 18 is 36. This cannot be cut. So we are left with only single point x equal to 5, and this point is a point of maximum. Therefore, for the box to have maximum volume, a square of length 5 centimeters should be cut, and V maximum will be equal to, now V is 45 minus 2x into 24 minus 2x into x. You can see the side sheet. So this is equal to 45 minus 2 into 5 is 10. 24 minus 2x. 2 into x is 10. And x is 5. So this is 35 into 14 into 5. This is equal to 2450 centimeter cube. This is the maximum volume of the box possible. Next is a square sheet of tin of side 24 centimeter is to be made into a box without top by cutting off squares from each corner and folding up the flaps. What should be the size of the square to be cut off so that the volume of the box is maximum possible? Also find the maximum volume. You can try this question yourself on similar lines. You can try this question as we did the earlier one and complete it. Now next question is, an open box with a square base is to be made out of a given quantity of cardboard of area c square units. Show that the maximum volume of the box is this much. Now base of the box is a square. So length and breadth are x and height is h. So volume of this box will be x square h. And area of the cardboard is c square. That is the area of the four sides of the box, and the base is c square. The box is open at the top. So area of four sides of the box. So area of four sides will be 4 into x is length into height, 4x h. And area of the base is x square. This must be equal to c square. Let this be 1 and this be 2. Now using 1 and 2 express this as a function of a single variable and proceed. You can try this yourself.